So I just opened my Twitter homepage. Does anyone want to take a guess how many requests are served by software caches in order to render this page for me? Any guess? 2, 5, 10, 20, 100? 80? Okay. Actually, the number of software caches that's being used in order to serve this website to me is in the range of thousands. Yeah, similarly, if you open like Amazon or Facebook, it's all in the range of thousands, sometimes even 10,000s. So you may wonder why there are so many caches involved to render this website. Let's look at a typical web application. So you have a web application. When the user opens the application, majority of the requests are sent to CDN, or content delivery networks. So content delivery networks deliver static data like image, videos, style sheets, or JavaScript directly from the edge of the internet to the user. A small portion of the requests get sent to the API gateway, where API gateway forwards requests to different services. Some of the services, for example, can be login service, ads service, user authentication service, etc. To serve those requests, they need to fetch data from the backend, where the backend can be either a database service or some storage servers. And as I mentioned earlier, fetching data from the backend is often very slow, so it's common to add a distributed key value cache in between the services and the backend. So at first glance, it seems there are only two caches in this diagram. So one on the left, which is the CDN, one on the right, which is this distributed key value cache. However, that's not true. If you look to the right of the distributed key value cache, there are storage servers, there are database servers. So they have page cache, they have database buffer pool. If you look to the left of this key value cache, there are different services. Many of them may have hot object cache to store hot objects, so you don't have to incur a networking round trip for every request. Further to the left, it's increasingly common to deploy a small cache at the edge inside the API gateway. So you do not have to send requests to the data center again and again if they are requesting the same results. Further to the left, inside the user device, either it is mobile phone or it is laptop, they usually have page cache, they have browser cache, and they sometimes have application level cache. So now if you look at this diagram, cache is in almost every box. Some of these caches are run in cloud data centers. Some of them are run at the edge, either in edge cluster or in end user device. These caches have consumed huge amount of resources. For example, one of the caching services at Google consumes petabytes of DRAM. While at Twitter, they operate hundreds of cache clusters using hundreds of terabytes of DRAM with hundreds of thousands of CPU cores. Similar reports can be seen from Meta, Pinterest, and many others. How should we make these software caches more sustainable and more efficient? There are two directions. In one direction, we can reduce the DRAM consumption. This is often achieved by caching more useful objects or caching more objects in the cache. And we call this efficient caching. In the other direction, we can reduce the number of CPU cores needed in order to serve the same workload. And this is often achieved by having faster and concurrent cache hits. And we call this fast and scalable caching. So for today's talk, I'm going to focus on cache eviction algorithms, because many different parts of cache affect cache performance and efficiency. But just for today's talk, I'm going to focus on eviction algorithms, because eviction algorithms exist in every cache. So eviction algorithms have been studied for over 6 decades now. So the common ones like FIFO or LRU, like everyone probably knows about it. So if you look at the history, of caching eviction algorithm study, most of them are LRU based, where LRU stands for least recently used. So all these algorithms in red, they are all LRU based. So as an LRU based algorithm, they have two problems. First, they are not scalable, because Upon each request, an LRU-based eviction algorithm needs to move the requested object to the head of queue, and this requires locking. And this global locking limits the scalability of LRU-based caches. And second, in the past 20 years, cache eviction algorithms have become increasingly complex. So you look at the ones on the right, they are very complex. They can't be implemented with tens of lines. It usually requires hundreds, even sometimes thousands of lines of code to implement those algorithms. And this hinders adoption. So if you look at what we really need in industry, so one of the kernel developers wrote that predicting which page will be accessed in the near future is tricky. And the kernel has evolved a number of mechanisms to improve its chance of getting right. But the kernel not only often gets it wrong, it also spends a lot of CPU time to make the incorrect decision. That's why we need a simple eviction algorithm. So speaking of simple eviction algorithm, there's one called FIFO, first in, first out. It's very simple. It's simpler than LRU and use fewer metadata because FIFO does not need to maintain any metadata at all. And upon each cache hit, FIFO does not require any computation. And this allows FIFO to scale to many CPU cores. Last but not least, FIFO is also flash-friendly because all the writes in FIFO are sequential writes. So if you want to implement eviction algorithm on flash, FIFO is your best choice. However, FIFO has one big drawback, which is its efficiency. So FIFO has a higher miss ratio compared to LRU and state-of-the-art eviction algorithms. So in the next 20 minutes, I'm going to introduce two techniques. One is called lazy promotion, one is called quick demotion. With these two techniques, FIFO-based eviction algorithm can be better than state-of-the-art eviction algorithm, both in terms of efficiency and scalability. Before I talk about these two techniques, let's first talk about existing eviction algorithms. I find that existing eviction algorithms all focus on promotion. So if we view the cache as a logically ordered queue, so on the left are objects preferred, on the right are objects are preferred for eviction. So if it is LRU, then left is the insertion point, then right is the eviction point. And upon each request, existing cache, most of the existing cache promote the object to the head of queue. And because it's eager promotion. And this promotion requires locking because this queue is often implemented using a doubly-linked list. And to mutate this, to move an object from the middle of queue to the head of queue, it requires changing multiple pointers, and this requires a lock. And this lock limits the scalability, as I mentioned earlier. What comes with eager promotion is passive demotion. So when an object is moved to the head of queue, all other objects are pushed down the queue. So this push-down process is very slow. So for a new object that enters at the left of the queue, it takes a long time for this new object to traverse through the queue before it gets evicted. So I argue that demotion should be the first-class citizen for cache eviction algorithm design, and we should use quick demotion, which quickly move an object from the middle of the queue to the tail of the queue. And we should use lazy promotion, which only promote an object before it gets evicted. Now let's look at these two techniques in detail. So lazy promotion, which only promote during eviction. So one simple example of lazy promotion is called FIFO reinsertion or clock or second chance. So these three algorithms refer to the same algorithm with different implementation. So clock uses a ring buffer, FIFO reinsertion uses a queue. So for each object in a FIFO reinsertion cache, we add one bit of metadata, whether it is 0 or 1. If it is 1, it means this object has been requested after insertion. If it is 0, it means this object has not been requested after insertion. So when an object is first inserted on the left, its bit is 0. Over time, if it gets another request, its bit sets to 1. At eviction time, we look at the tail object. If the bit is 1, it gets reinserted to the head with the bit reset to 0, like this. And then we check the next object. If the if this object has a bit 0, then it gets evicted. So that's a very simple algorithm. And insertion always happens at the left or at the head. So compared to LRU, or compared to eager promotion, FIFO reinsertion has a few benefits. First, it incurs net computation. Let's say if you have a popular object gets millions of requests, then FIFO reinsertion does not need to update any object metadata for most of the requests, because only the first request requires changing the bit from 0 to 1, right? So it incurs net computation. Second, there's no global locking required. This allows FIFO reinsertion to achieve better scalability. And third, because we know that we have more information at eviction time. So we know that how many times this object has been requested and when it is last time requested. So with this more information, we can make a better decision. And we find that FIFO reinsertion compared to LRU is actually more efficient, which is contrary to conventional wisdom. Let's look at some results. So in this figure, Y shows fraction of traces with lower miss ratio, X shows 10 different data sets. So each data set has from a few traces to a few thousand traces. So these are the traces open sourced by different companies. They cover both block cache, key value cache, and CDN cache. So in this figure, if you compare the two parts, the bar, the ones with a longer bar means that this algorithm is better on more traces. For example, for these three data sets, FIFO reinsertion is strictly better than LRU on all traces in this data set. For other data set, even though it is not, FIFO reinsertion is not 100% better on all traces, it's still better than LRU on most traces, because we see that it's all more than 50%, except the last two. So the last two, FIFO reinsertion does not work that well because this is from social network, and data in the cache gets multiple requests. And using one bit to distinguish between unpopular objects and popular objects is not sufficient. We observe that if we increase the number of bits per object to 2 bits, then for these two data sets, FIFO reinsertion is also significantly better than LRU. So you may wonder, why is FIFO reinsertion more efficient than LRU? Because this is like different from conventional wisdom suggests, right? Why all of a sudden we find something different? Well, our observation is that FIFO reinsertion can evict new objects faster. For example, if we have the following request sequence, B, N, A, X, and at this state, if we look at this cache queue, where the left is insertion, the right is eviction. And the blue one shows this object has not been visited, meaning that the bit is 0, while the orange one means that the object has been visited. If you use LRU, for this new object gets inserted at head with this object N, only A and X will push N down the queue, because A is requested after N, and X is requested after N. Only these two objects gets push N down the queue for LRU. But if you use FIFO reinsertion, not only A and X push these new objects down the queue, some objects that gets requested previously also push this object down the queue. For example, object B. Because object B will get reinserted when it gets evicted. Then this also pushes new objects down the queue. So in other words, new objects in FIFO reinsertion traverse the queue much faster compared to LRU. And this allows FIFO reinsertion to be better than LRU. So you may wonder why evicting new objects faster is better, right? This brings the quick demotion idea. So the idea of quick demotion is to quickly evict new objects. The motivation behind quick demotion is that we find that one-hit wonders are very common in cache workloads. So one-hit wonders are objects that gets only requested once in a request sequence. And we find that for cache workloads, shorter request sequence tend to have larger one-hit wonder ratio. Let's look at one toy example. So in this example, I have 17 requests for object A, B, C, D, E. And in total, there are 5 objects, and only one of them is one hit vendor from 1 to 7, which is this object, object E here. And all other objects have at least 2 requests. And the one hit vendor ratio for this full request sequence is 20%. If you look at a shorter request sequence, say from 1 to 7, then there are 4 objects being requested, A, B, C, D, and 2 of them are one hit vendors, which is this object C and D. And the one hit vendor ratio increased to 50%. So this toy example illustrates that shorter request sequences tend to have larger one hit vendor ratio. While this is a toy example, let's look at some synthetic workloads and production workloads. So this figure on the left shows how one hit vendor ratio change with the sequence length. So on the right side is the full request sequence. On the left is shorter request sequence. And I'm showing 4 different synthetic workloads with different skewness. We can see that the one hit vendor ratio increases very quickly if we go from the right side to the left. At 1/10 of these traces, the one hit vendor ratio is around 80% across different skewness. Well, this is synthetic workload. Now let's look at production workloads. So I'm showing 2 production workloads, one from Twitter and one from Microsoft Research. Same, it's a y-axis is the same, which shows the one hit vendor ratio. X shows the fraction of objects in the trace. So on the right-hand side, at 100%, or this 1, is the full trace, which is weak now. On the left, it means shorter trace. We can see that for full trace, the one hit vendor ratio is it's not huge. It's still pretty large. Like for example, this one is like 15 to 17%. This one is like 30%. However, if we look at short request sequence, say 1/10 of the weak long trace, then the one hit vendor ratio increased to for the Microsoft trace increased to 75%, and for the Twitter trace increased to almost 30%. So you may wonder, why do we care about shorter request sequence, right? We care about shorter request sequence because a cache cannot see the full request sequence. So it can't see the full week-long request sequence. So it has to make eviction decisions after it sees a shorter request sequence. That's why we care about shorter request sequence. We further measured the one hit vendor ratio of week-long traces at 10% length on over 6,000 traces from 12 companies. And we find the one hit vendor ratio, the mean one hit vendor ratio is 72%. So this means that 72% of the objects are only used once. And most of objects are not used before being evicted. To validate this, we run cache simulations. So we use the different eviction algorithms, but here I'm only showing LRU. So in this figure, Y shows the fraction of evicted objects, X shows different cache sizes. And different parts of the bar shows the frequency of evicted objects. Frequency 1 means that the object is not reused after insertion, while frequency 2 means that the object gets 1 request after insertion. We can see that across different cache sizes, even at a very large cache size, this 7.5 means that 50% of the trace footprint. Say if the trace if there are in total like 1 million objects gets requested in the trace, then this 0.5 means that the cache size is 500K. We can see that for different cache sizes, majority of the objects gets evicted from the cache have frequency 1, meaning that they are not reused. So, so this is on the Microsoft Research workloads. Similarly, we can observe we can have similar observations on the Twitter workload. So most of our objects do not get reused after insertion. So in other words, we probably should not insert those objects into the cache if we know that they are not going to be reused. But the problem is that we don't know whether an object is going to be reused or not when they are going to be inserted. So so if you look at the existing state-of-art eviction algorithms, they share one common thing. First, there are different state-of-arts being proposed and being designed in the past 2 decades. many of them are very complex, using multiple queues, complex metrics, or even sometimes use machine learning to help with eviction. However, if you implement those eviction algorithms and do some measurement, you will find that the secret sauce of all these state-of-the-art eviction algorithms is that they evict objects very aggressive. So after a new object gets inserted, they quickly evict those objects using different approaches. And this turns out to be the secret sauce of all those algorithms. So with this, you can probably guess how we should design a better eviction algorithm that's simpler while meanwhile being very effective. So let me introduce S3 FIFO. So it stands for Simple Scalable Caching with 3 static FIFO queues. So it has nothing to do with AWS S3. So it's just like 3, we have 3 in the keyword here. That's why it's called S3. So S3 FIFO, as the name suggests, use 3 FIFO queues. It's a very simple design. So it has a small queue, a ghost queue, and a main FIFO queue, all being FIFO. So the small queue uses 10% of cache space, the main queue uses 90% of cache space, and the ghost queue only stores metadata, so does not store data. So for each object in the cache, we associate with 2 bits of metadata, which acts as a capped frequency counter. So basically, it can count from 0 to up to 3. And upon a cache hit, the counter increment by 1 until it reaches 3. Upon a cache miss, we check whether the requested object is tracked in the ghost or not. If it is not in the ghost, the object is inserted into the small queue. However, if the object is tracked in the ghost, then it gets inserted into the main FIFO queue. Inserting objects into a small queue and the main FIFO queue may trigger eviction. And eviction from the small queue happens at the tail. So we look at the tail object, we check its frequency. If the frequency is no more than 1, then it gets evicted, and this object ID or block ID is tracked in the ghost. Otherwise, it gets reinserted into the main FIFO queue at the head. So inserting into the main FIFO queue may also trigger eviction. So this is main FIFO queue use FIFO reinsertion. So we look at the tail object. If the counter is more than 0, it gets reinserted with the counter decrement by 1. So this is a very simple algorithm. So if you look at this algorithm and think about the 2 techniques I mentioned a few minutes ago, one is quick demotion, one is lazy promotion. The small FIFO queue actually is used for quick demotion. Because if a new object does not get a second request in the small queue, then it gets evicted very quickly. So it doesn't need to traverse through the whole cache before it gets evicted. And the main FIFO queue use lazy promotion because it uses reinsertion to keep popular objects in the cache. So with these 2 techniques, I'm going to show you that S3 FIFO can actually outperform state-of-the-art eviction algorithm, both in terms of miss ratio and throughput. Any questions so far? That's a great question. So the question is that whether there's an assumption that the popularity follows Ziphian. So when we started, yes, we had the assumption, but later we realized, most web workloads follow Ziphian distribution, but broad cache workloads usually do not, and it do not strictly follow Ziphian because of scans and various other patterns. But even with scans, we find that one-hit vendor, the observation of one-hit vendor still exists in broad cache workloads. So what we end up leveraging is the high one-hit vendor ratio instead of Ziphian. So basically Ziphian will cause high one-hit vendor ratio, but we don't really need Ziphian. We only need high one-hit vendor ratio. Yeah. So the ghost queue here, we use 90%, which allow us to store 19% of the block ID. Basically, if the cache can store, say, 1 million objects, and then the ghost queue can store 900K object IDs. notice that the ghost queue does not store data. So it only keeps track of the object ID or the block ID. So it's much smaller than the cache. Yeah. Okay. So yeah, so S354 is a simple algorithm, and it turns out it's actually robust than existing adaptive algorithms, which I'm going to show later. Because the static queues surprisingly turns out to be more robust. And it's also fast because there's no metadata update for most requests. And as a result, it's also scalable because there's no global locking required. And use tiny object metadata, which is only 2 bits. And it's also flash friendly because all the writes in S354 is sequential write. Although I describe S354 using 354 queues, the actual implementation can either use 1 or 2 or 354 queues. So our implementation in CacheLib actually used 254 queues. Okay, so now let me talk about evaluation. So we used 14 data sets with over 6,000 traces. So this is by far the largest cache eviction algorithm study. Compared to previous study, it's millions times larger in terms of request count. So these traces are from different companies, and in total there are over 800 binary requests. And they were collected between 2007 and 2023. It covers both block cache workloads, key value cache workloads, and object cache workloads. And we used NIP Cache Sim, which is a simulation platform, and we also implement inside CacheLib. Because we have so many traces, we can't really show the hit ratio or miss ratio for each trace because we're going to have like thousands of figures. So we use the metric called miss ratio reduction from FIFO. So basically, for each trace, we run a FIFO and we run a different algorithm, and we compare the miss ratio of the 2 algorithms, and we see how much miss ratio can the new algorithm reduce from FIFO. Basically, we use FIFO as a baseline. So the higher reduction, the better. Okay, so in this figure, the y-axis shows different data sets. X-axis shows the mean miss ratio reduction from FIFO on each data set. So the right-hand side is better. And I have different state-of-the-art eviction algorithms in this figure: ARC, tiny LRU, caches, 2Q, nurse, and LHD. So if you look at this figure right now, before I show S354, different algorithms perform the best on different datasets. For some datasets, 2Q is the best. For some, ARC is the best. For some of them, nurse is the best. Now let me show you S354. So this is S354. Compared to existing state-of-the-art eviction algorithms, S354 actually performs the best on most of the datasets. I think we have 14 datasets here. I think on 12 of them, S354 is the best eviction algorithm. And yeah, so this shows that S354 is not only efficient, but also robust. So that's miss ratio. So we do have more results in the paper, and yeah, I do also have other results. If you're interested, you can talk to me after the talk. Now let me talk about throughput. So as a FIFO-based eviction algorithm, the throughput of S354 is amazing. It scales with the number of threads. So in this figure, Y shows the throughput in millions of operations the cache can serve per second. X shows the number of threads. And I'm comparing S354 with LRU and optimized LRU. So, because LRU requires a lock at each request or each cache hit. So it's not scalable at all. And we implement this inside CacheLib because scalability is very important for meta workloads. So the CacheLib team spent a lot of effort to improve the scalability. So it used a lot of different techniques, which is this optimized LRU stands for. So with all those techniques and optimizations, the optimized LRU compared to strict LRU is already much better. However, compared to S354, the optimized LRU still has much lower throughput. Because in S354, we do not require locking at all. So all operations either can be implemented using atomic or does not require any synchronization. That's why S354 can scale with the number of threads. So at a single thread, S354 is the fastest algorithm because for most requests, it does not need to mutate any state. And at 16 threads, S354 achieves 6 times higher throughput compared to optimized LRU. So that's throughput and scalability. So to give a quick recap of this part, so SOA-FIFO stands for Simple Scalable Caching with 3 static FIFO queues. So I talk about the prevalence of one-hit wonders, and I show that using a small FIFO queue can quickly remove one-hit wonders, and this allows SOA-FIFO to achieve superior efficiency. And SOA-FIFO also uses reinsertion to keep popular objects in the cache. And reinsertion allows SOA-FIFO to achieve both good efficiency and good scalability. So this is the first time that we showed FIFO queues alone is sufficient to design efficient eviction algorithms. And SOA-FIFO has already been deployed at many different companies, including Google. A variant of SOA-FIFO is also deployed at VMware and Red Panda and many others. And also, on the open source side, there has been more than 10 open source libraries implementing SOA-FIFO in many different programming languages. So that's SOA-FIFO. So SOA-FIFO improves the efficiency and scalability of existing eviction algorithm. However, it's not the simplest algorithm yet. Can we further reduce the simplicity, reduce the complexity of eviction algorithm? This brings a SIF, which is an eviction algorithm that's simpler than LRU while achieving state-of-the-art efficiency. So earlier I mentioned that the secret to design efficient eviction algorithm, one is called lazy promotion, one is called quick demotion. So lazy promotion is used to retain popular objects with minimal effort, and quick demotion is used to quickly remove new objects, because new objects tend to be one-hit wonders. Okay, now let me show you how SIF works. But before that, let me first show you how let me give a quick recap on how FIFO reinsertion works. So FIFO reinsertion uses 1 bit of metadata, and you reinsert the objects at the tail at the eviction time. And SIF requires a small change from FIFO reinsertion. So SIF also uses a FIFO queue, and for each object in the queue is associated with 1 bit of metadata. However, it does not use reinsertion to keep objects that we want to retain. Instead, it uses a moving hand from the tail to the head. So, for example, at this stage, you look at the tail of the object has bit 1, so we want to retain this object. So instead of reinserting this object to the head, it keeps the object at the original position, and it moves the hand to next position. Then it checks the next objects at next position, and it is 0, it gets evicted. Then the hand, next time when we need to evict again, the hand keeps moving towards the left or towards the head until it reaches the head, and it gets wrapped up to the tail. So compared to FIFO reinsertion, this is very similar, except that we use the moving hand. And insertion always happens. Insertion always happens at head, similar to FIFO reinsertion. So yeah, basically we change the way we retain objects. Instead of reinsertion, we keep it at older positions and use the moving hand to find the next objects to evict. So compared to existing algorithm, SIF is extremely simple. It has 0 parameter at all, and it's fast and scalable because it does not require knocking upon cache hit, and also use small per object metadata. Besides this, it's also TTL friendly. So if your workload has TTL or time to leave, because objects in the queue are sorted by insertion time, and if they have the same TTL, they're also sorted by expiration time. So this makes SIF friendly to workloads that requires TTL. So you may wonder, why does such a small change, or why does such simple algorithm work? So first, SIF can retain popular objects very effectively. So as the hand moves from the tail to the head, popular objects which has bit 1 gets retained. And SIF can also evict new objects very quickly. So as the hand moves towards the head, it will stay at head for an extended period of time, and new objects which gets inserted here gets evicted very quickly. And last, sieve can actually separate new and old objects. So the objects after the hand are always new old objects, meaning that this object has already survived at least one round, while objects at the head are always new objects. So this separation allows the algorithm to easily decide which objects are more valuable to retain in the cache. Now let's look at some results. So for this evaluation, we focused on web cache workloads. However, later I will show that sieve does not only work on web workloads. We find that it also works on multi-tenanted block cache workloads. Now let's look at web cache workloads first. So in this figure, Y shows miss ratio reduction from FIFO, the same metric. And we show a box plot here. And x-axis shows different eviction algorithm. And this first bar is sieve. We can see that compared to existing state-of-art eviction algorithm, sieve achieves similar or slightly better miss ratio reduction. And specifically, sieve reduced FIFO's miss ratio by more than 42% for 10% of the trace, which is this top whisker, and with a mean of 21%. Different cache workloads. So this one is from a CDN, this one from a second CDN. They have different number of traces and different number of requests. We see that sieve also performs better than state-of-art eviction algorithms. So besides these two production workloads or two production datasets, we find that sieve also achieves the lowest miss ratio on the well-studied CVM workloads. So that shows request miss ratio, because it measures how many requests are cache misses or cache hits. But for some systems, we also care about byte miss ratio, because retrieving a large object costs longer time. So here we measured byte miss ratio. And we find that sieve actually achieves even better performance compared to state-of-art eviction algorithms. So that's byte miss ratio on the left. And we further compared sieve with with a new state-of-art called LRU. So LRU is a machine learning-based eviction algorithm. And because it uses machine learning, it runs very slow. So we can't run it on like few thousand traces because it takes years to run it. So we only run it on this wiki trace, which is used in the LRU paper. And we basically use the same trace, and we compare sieve with LRU and several state-of-art. And we find that only at a very small cache size, like 1% of the working set or the trace footprint, LRU shows some advantage. As long as we have slightly larger cache size, sieve is actually better than a machine learning-based eviction algorithm. Why? Because when we have relatively large cache size, most of the objects in the cache only gets one or two requests. How should you learn about the future behavior if you only have one request, right? That's why machine learning falls short for this. Okay, so that's efficiency. Now let me talk about throughput. Because sieve does not require locking at each cache hit, it also achieves superior scalability. So similarly, in this figure, Y shows throughput, X shows number of threads. And we can see that sieve compared to LRU and optimized LRU achieves better throughput at both single thread and 16 threads. Okay, because sieve is easy to implement, we implement sieve in a few popular open source production cache libraries in different languages. And all those cache libraries use LRU, or is recently used. And we find that it takes less than 20 lines, around 20 lines, to modify LRU to use sieve. So sieve was published earlier this year, and it has already been adopted by many different systems and open source libraries. So besides using sieve as a cache eviction algorithm, if you want better performance or better efficiency, you can also compose sieve with other eviction algorithms. For example, Nika, 2Q, and ARC are different algorithms, different state-of-art eviction algorithms. And Nika uses LRU plus LRFU with some machine learning technique. And 2Q uses LRU plus FIFO, ARC uses two LRU queues and two ghost queues. We find that by replacing the LRU queue with sieve, we can actually achieve better efficiency. For example, this is Nika. Like the orange one is Nika. By replacing the LRU in Nika with sieve, we can achieve a better efficiency. Similarly, for ARC, if we replace the LRU with sieve, it also achieves better efficiency. So if we want better efficiency, you can use sieve to design even better eviction algorithms. Yeah, so as I mentioned earlier, sieve is already available in more than 20 open source cache libraries with more than 12 programming languages. And there have also been many production systems that have already integrated sieves. And one of the users that used sieve reported that after switching from tiny LRU to sieve, he observed 33 times mismatch reduction with 16% CPU saving. Yeah, so that's some user report. So as a summary, so today I talked about two techniques. One is lazy promotion, one is quick demotion. And I talked about S3 FIFO, which is a simple eviction algorithm that's only use FIFO queues, and use small queue to filter out one-hit vendors, and use min queue to keep most of objects in the cache. And in the last part of today's talk, I talked about sieve, which is the simplest algorithm that combines lazy promotion and quick demotion. Yeah, so if you want to know more about S3 FIFO and sieve, we have two websites. Just here, you can just learn more about these two algorithms. So yeah, as I mentioned, sieve has already been, both algorithms have already been adopted in many companies, and this won't happen without collaborations with many industry partners. And as one of the few academics in SDC, I really value collaborations. So collaborations allow our collaborators to try out new ideas early on and give us feedbacks, and also sometimes allow us to share workloads and have earlier hardware access. And we have collaborated with many different companies. So if you're interested in trying out those algorithms or you're interested in collaboration, feel free to send me an email. Yeah. With that, I'm happy to take questions. Thank you. Yeah, that's a great part. So the question is about there are other data structures in the cache that requires locking. Yeah, that's I agree with that. So usually in many caches, you use hash table for indexing. And hash table, most of the hash table implementations today use locking. But they use fine-grained locking, which somehow reduce the locking of contention. But there are also lock-free hash tables, but they are not. I think most of the production systems do not use lock-free hash tables, but they do exist. Yeah, but back to your question, yes, there are data structures that may require locking. Here, I'm only focus on the data structure that maintains the ordering of objects in the cache, meaning that the part that's responsible for cache eviction. Yeah, and that part does not require locking in S3 FIFO and sieve. Does that answer the question?
After that kind of skip the page, if there is no TTL, when do we evict the
So the question is about when a page is skipped in sieve, if there's no TTL, when is the page evicted? So sieve does not require the use of TTL, although it is friendly to TTL. So for a workload that does not have TTL, sieve, after the hand moves, it checks the page and keep retained in the cache. It will stay there for some period of time until the hand moves to the head and wraps around. So once the wraps around, it will check the page again. So this, yeah. Any other question?
When do you move the hand? Like every time you
Yeah, so the hand moves at eviction. So at eviction, we check the objects pointed by the hand. And if the object has bit 0, the hand moves towards the head. If it has, if it has bit 1, the hand moves towards the head. If it is 0, it gets evicted. Next time, we look at the same position, and if the bit is 0, it gets evicted. If it is 1, it moves towards the left. So basically, yeah, the hand moves at the eviction time.
When you look at the scalability on CPU, you mentioned optimized LRU. What's the high-level idea?
The cache lib use a few different ideas to optimize LRU. One of them is to delay promotion. For example, if an object gets promoted in the past minute, it does not promote again. This turns out to be very effective. That's one technique. A second technique is use better locking. So they basically combine the critical sections. So you don't have to lock and do a little bit of things, then unlock. Because locking is relatively expensive. If you can combine multiple critical sections together and lock once, you will save some CPU overhead and also improve the scalability. There are other smaller ideas in cache lib that also improve scalability. Yeah, but these are the two main ideas. So that's a great question. So the question is about whether we use the eviction to evict objects from DRAM to flash. So in this evaluation, we did not use flash cache. So we just use DRAM cache. Yeah. That's a great question. So the question is, the question is about the comparison between S3FIFO and SIF. So comparing between these two, S3FIFO is definitely more complex. It's also more robust. So when we wrote the paper, we said that SIF only works on web cache workloads, meaning that page cache does not work well. But later we observed that for multi-tenant block cache workloads, SIF also works really well. So we used two block cache workloads, one from Alibaba and one from Tencent. They are both EBS type of workloads. We find that on these two workloads, SIF also works very well. But back to your question, between S3FIFO and SIF, SIF is simpler, but SIF is not as robust as S3FIFO. Their workloads, SIF does not work well. So for some of the old workloads from like 20 years ago, mostly block cache workloads, we find that SIF can be really bad, like in terms of miss ratio. Yeah. Any more questions? Yeah. Sorry, can you repeat?
Were any of the traces specifically from CDNs?
Yeah, so the question is about whether any of the traces are from CDNs. Yeah, we do have, we collaborate with two CDN companies, and we do obtain traces from them. We have two DSS, one contains over 1,000 traces, one contains over 200 traces. Yeah. So basically the dataset is very diverse. It covers different type of workloads, and also for each workload, it also comes from different companies. Yeah, I think we are out of time. If you have other questions, feel free to come to talk to me.